NENOMATICA, where mathematics meets YouTube excellence. We will solve radical inequalities with even roots by following a precise two-step algorithm. Step 1 handles the strict inequality. Step 2 handles the non-strict inequality. Step 1. For the strict case, square root of f of x is less than g of x. We must satisfy three conditions at the same time. F of x is greater than or equal to 0, g of x is strictly positive, and f of x is less than the square of g of x. Step 2. For the non-strict case, square root of f of x is less than or equal to g of x. We again require f of x to be greater than or equal to 0, g of x to be non-negative, and f of x less than or equal to the square of g of x. Now, let us apply the algorithm to a worked example that uses the strict case. According to step 1, we create a system of three conditions. First, 2x plus 3 is greater than or equal to 0. Second, x plus 1 is strictly greater than 0. Third, 2x plus 3 is less than the square of x plus 1. Let's solve each, and then intersect the results. Solve the first two easy inequalities. X is greater than or equal to negative 1.5, and x is greater than negative 1. Now solve the third inequality. 2x plus 3 less than x plus 1 quantity squared becomes 0 is less than x squared minus 2, or equivalently x squared minus 2 is greater than 0. That gives x less than negative square root of 2, or x greater than square root of 2. Intersect all three x greater than or equal to negative 1.5, x greater than negative 1, and x either less than negative square root of 2 or greater than square root of 2. Only the region x greater than square root of 2 survives. So the solution set is x greater than square root of 2. Quick challenge. Pause and predict the steps for a non-strict inequality before we reveal them. Now, a non-strict example that follows step 2. Build the system using the non-strict rule. First, x plus 4 is greater than or equal to 0. Second, 2 minus x is greater than or equal to 0. Third, x plus 4 is less than or equal to the square of 2 minus x. Solve the first two x greater than or equal to negative 4, and x less than or equal to 2. Now, the third inequality, x plus 4 less than or equal to quantity 2 minus x squared, gives 0 less than or equal to x squared minus 5x, or x times x minus 5 greater than or equal to 0. The solution is x less than or equal to 0 or x greater than or equal to 5. Intersect all three. From negative 4 to 2, intersected with x less than or equal to 0 or x greater than or equal to 5, yields the interval from negative 4 to 0, inclusive. That is the final solution. Example, we will solve the inequality square root of x plus 5 is less than 1 minus x following a disciplined, step-by-step algorithm. Step 1, find the domain of the square root. The inside must be non-negative. So x plus 5 is greater than or equal to 0, which means x is greater than or equal to negative 5. We call this d sub 1. Step 2, ensure the right side is positive because we will square both sides. 1 minus x must be strictly positive. Therefore, x is less than 1. We call this d sub 2. Step 3, square both sides within the allowed domain. Start from square root of x plus 5, less than 1 minus x. Squaring gives x plus 5, less than 1 minus 2x plus x squared. Move everything to the right to get 0 less than x squared minus 3x minus 4, or equivalently x squared minus 3x minus 4 is greater than 0. Step 4, factor the quadratic and find intervals. Factorization gives x squared minus 3x minus 4 equals left parenthesis x minus 4 right parenthesis times left parenthesis x plus 1 right parenthesis. Since the parabola opens up, the expression is greater than 0 when x is less than negative 1 or x is greater than 4. We call this d sub 3. Step 5, intersect all restrictions. We take d1 intersect d2 intersect d3. First, d1 intersect d2 equals the interval from negative 5 to 1 open at 1. Intersecting that with d3 leaves the interval from negative 5 up to, but not including negative 1. Endpoint check. At x equals negative 1, both sides equal 2, so the strict inequality fails. Negative 1 is excluded. At x equals negative 5, we get 0 less than 6, which is true. Negative 5 is included. Therefore, The solution set to the inequality is the interval from -5 to -1, not including -1. Quick challenge. Pick x equals -3 from the solution set and x equals 0 from outside the set. Verify the original inequality in each case. Summary. We enforce the domain of the square root, guaranteed the right side was positive, squared both sides, solved the quadratic inequality by factoring, and intersected all restrictions. Example. We will solve the inequality. The square root of x squared minus 3x minus 10 is less than 8 minus x. We will strictly follow 4 steps. Domain of the square root, positivity of the right side, square both sides, and intersect all conditions. Step 1. The square root requires its radicand to be non-negative. Say x squared minus 3x minus 10 is greater than or equal to 0. Factor to find the critical numbers at -2 and 5. Therefore, the first domain set is all x less than or equal to -2 or x greater than or equal to 5. Step 2. Because the left side is a square root, it is non-negative. To keep the inequality direction valid, when we square both sides, the right side must be strictly positive. So 8 minus x is greater than 0, which gives x less than 8. That is our second domain set. Step 3. Now we can safely square both sides. The rule is, if 8 minus x is positive, then square root a less than b implies a less than b squared. We get x squared minus 3x minus 10 is less than the square of 8 minus x. Expand and simplify to 13x minus 74 is less than 0, so x is less than 74 over 13. That defines our third domain set. Step 4. Intersect all 3 conditions to obtain the solution set. Intersect D1, D2, and D3. Because 74 over 13 is about 5.69, the final solution is all x less than or equal to -2 or x from 5 inclusive up to 74 over 13 exclusive. We will also visualize this on a number line. Quick challenge. Can you estimate the decimal value of 74 divided by 13 and mark it on the number line between 5 and 6? We will solve the inequality. Square root of 52 minus x squared over 2 minus x is less than 1. First, let's display the problem as an example in bold orange. Step 1. We set domain conditions and translate the inequality into a system that respects the denominator's sign and the square root's domain. When the denominator is positive, 2 minus x greater than 0, we can multiply without reversing the inequality, giving the square root strictly less than 2 minus x. Let's show this rule box and the system. Step 2. From 2 minus x greater than 0, we get x less than 2. Step 3. The radicand must be non-negative. So 52 minus x squared is greater than or equal to 0, which means x is between -2 root 13 and +2 root 13 inclusive. Step 4. With 2 minus x positive, square both sides of the inequality square root of 52 minus x squared less than 2 minus x, then simplify. Step 5. Solve the quadratic inequality x squared minus 2x minus 24 greater than 0. The roots are -4 and 6, and the inequality holds outside the roots x less than -4 or x greater than 6. Step 6. Intersect all conditions from this case, x less than 2, x in the closed interval from -2 root 13 to 2 root 13, and x less than -4 or x greater than 6. Only the branch x less than -4 survives, giving D1 equals bracket -2 root 13, comma, -4 parenthesis. Step 7. Consider the second case, when the denominator is negative, then 2 minus x is less than 0, and multiplying by it reverses the inequality, so the square root is greater than 2 minus x. Step 8. From 2 minus x less than 0, we get x greater than 2. Step 9. The radicand condition remains the same, x is between -2 root 13 and +2 root 13 inclusive. Step 10. Because x is greater than 2 and the right side 2 minus x is negative, the inequality square root greater than a negative number is automatically true. So we only keep the domain cuts, giving D2 equals open parenthesis 2, comma 2 root 13 bracket. Step 11. The full solution is the union of the two intervals. Domain of the square root. The radicand must be greater than or equal to 0. We write f of x equals x squared minus x minus 12 is greater than or equal to 0. Then we factor it as parenthesis x minus 4 close parenthesis times parenthesis x plus 3 close parenthesis greater than or equal to 0. From the sign chart, x is in negative infinity to negative 3 including negative 3, union 4 to infinity including 4. Step 2. Since the left side is a square root, it is non-negative. For the inequality to hold, the right side x must be strictly positive. We record g of x equals x greater than 0. Step 3. Square both sides. Because x is positive, squaring preserves the inequality direction. We use the rule f of x less than g of x squared implies x squared minus x minus 12 is less than x squared, which simplifies to x greater than negative 12. Step 4. Intersect all constraints. We combine the Radicand domain, the positivity condition x greater than 0, and the simplified condition x greater than negative 12. The intersection is from 4 to infinity, including 4. Step 5. State the final solution set clearly. The set of all real numbers x such that the inequality holds is the closed interval from 4 to infinity. Summary. First, show the example label and the problem in orange. Step 1. The expression inside a square root must be greater than or equal to 0. We display the rule. Step 1 title. Write the product condition and solve for x intervals using the zeros at negative 4 and 1/2. Show the domain from this step, union of negative infinity to negative 4 closed, with 1/2 to infinity. Step 2. Since the right side is x plus 4, for the inequality to make sense after squaring, we require x plus 4 strictly positive. Show the rule box. Add the step 2 title. Derive x greater than negative 4. Step 3. With the radicand non-negative and x plus 4 positive, we may square both sides, and we can divide by x plus 4 without reversing the inequality. Show the rule box. Add the step 3 title. Write the squared inequality. Divide by x plus 4 to get 2x minus 1 less than x plus 4. Solve to obtain x less than 5. And keep the condition x greater than negative 4 from step 2, giving negative 4 less than x less than 5. Step 4. Intersect the domain from steps 1 and 2 with the inequality result from step 3. Show the rule box. Add the step 4 title. Compute the intersection to get the final solution set from 1/2 inclusive to 5 exclusive. Present the answer in green. Summary. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.